I'm David Patschke. I'm a data scientist at Dell EMC in Austin, Texas. So just to give you guys a little point of reference of this talk, about 3 or 4 weeks ago, I gave a very similar talk at AnacondaCon conference in Austin. Feedback that I got is like, man, that was really good, but it is that was pretty technical. So what do they do? Like I tell Domino, they schedule me right after lunch. So this is pretty technical. I tried to tone it down a bit, but also have added something at the end that should hopefully be a little bit more practical. So, purpose of the talk, I want to introduce a feature evaluation method that I've used in a past life. Can't say I use it too much at Dell, but it's Monte Carlo permutation testing, and the premise of it is it's a parallelizable feature evaluation method. And the second part, or the bonus, aside from AnacondaCon, is I have created actually a class, the MCPT Feature Evaluator Python class, that wraps a lot of that functionality that is both pandas and scikit-learn compatible. And under the hood, it utilizes Python's Numba package. So if you're not familiar with Numba and you do high-performance computing, I highly recommend that you check it out. It's a cross-platform, LLVM compiled native Python implementation that basically you wrap it with decorators. All of the code that you write is pretty much in native Python with just a few specific Numba functions. One of the recent capabilities that they've added in there is this parallel accelerator functionality with Intel. So you get practically free multi-threaded parallelization capability with parallel accelerator. It sits in a single memory space, and for those of you like Dell, we're huge Windows, and we work in Windows quite a bit. This is all agnostic to operating system, totally cross-platform. So little smiley face, we work in Windows, and I can get that same multi-threaded single memory space functionality. If you want to take a look at a blog post which will much better describe some of the recent advances, there's a blog post there. Finally, warning, this is absolutely a work in progress. I did a lot of this work within the last couple of weeks because I wanted to create a kind of a more practical implementation to really leverage a lot of the work that I've been doing. So as a result, I have some limited documentation that you'll see and my formal test cases. And being a former software developer, I give myself a frowny face for that. So. Okay, first want to give credit where credit is due. This concept I actually picked up from Dr. Timothy Masters, who has 2 books that are available. Assessing and Improving Prediction Classification and Data Mining Algorithms in C++. If you put models into production, I can't recommend this Assessing and Improving Prediction and Classification highly enough. It discusses some things in there that really don't see in too many other texts, specifically calculating model gain above inherent model bias, doing some bootstrap estimations. And then the data mining algorithms, I'll discuss a little bit of what's in there during this talk, having implemented it in Python. But also deals with high-dimensional and small-size data set evaluation. So again, can't recommend that highly enough. And the other credit attribution, Numba developers, again, check out Numba if you haven't seen that, and the Intel developers for contributing the parallel accelerator functionality. Actually, there's another slide that I should probably put in there. Need to thank my wife. She travels a lot for a living, but was putting up with me, especially over Memorial Day weekend as I was finishing up doing this Python class. So the problem that I want to present here and discuss is that, okay, I'm a user and I have a high-dimensional data set. And I'll say that that's uppercase X. And as quickly as I can, I want to identify which of the independent variables that are in that high-dimensional data set, which one of those have have a strong relationship with a dependent variable, and I'll name that Y0. So again, I'm going to provide a few visualizations of this, so hopefully it's easier to step along, but we have our matrix X and our target variable Y. So what are some of the popular feature evaluations that are present, especially in the Python ecosystem? So within scikit-learn, you have your information measures that are listed here. And so the mutual information classification and regression piece are somewhat unique. There's a unique implementation with them that it's k-nearest neighbors. And I've also implemented this here within Numba. So I'll go over that as well too. The lasso regression, so using lasso CVM to select from model, you end up determining the variables that have non-zero coefficients, and those are some of the variables as a system that can be pulled out as being meaningful to your target variable. And then lastly, there's the tree methods, random forests, and your boosted decision trees. There's also a method that leverages random forests called Baruda, and actually the method that I'm going to describe is very similar to Baruda in the sense that you permute your target variables a bunch of times and then determine from there which of your independent variables are most relevant to your target variable. So what are some of the feature evaluation challenges in a very high dimensional data space? Well, first off, your time to perform the evaluation can be incredibly costly. Secondly, because you have so many variables, there's just a natural probability that if you only look at your information measures by themselves, that you could pick up one of those variables by random luck. And the worst part about that is if it looks like it's good and you put these random luck variables into a model, that model is going to say, hey, there's signal in there, and I'm going to try and model to that what would be noise otherwise. So you have a model that is modeling noise, and that leads to models that tend to not generalize well, i.e. overfit. So again, right, trying to figure out a solution, high dimensional data set, how can I accurately and as quickly as possible determine like where I need to go from a feature evaluation? So my proposed solution, or Dr. Master's proposed solution, Monte Carlo permutation tested. So what is MCPT? I'm going to run through this real quick. Hang in because I'm going to do some visualizations along here too. So first I want to identify a pretty simple information measure that I want to use as my feature evaluation. So I'm going to stick to the univariate space right now, but this can certainly be extended to bivariate or multivariate. So the two information measures we're going to use are mutual information and uncertainty reduction. If you haven't heard of uncertainty reduction, I will go over that. It's very much related to mutual information. Okay. I'm going to take my target variable and I'm going to permute that k number of times, and k is a number that you choose in order to determine robustness. And so I'm going to name those yp1 through ypk, the target variables. And then for the information calculation, I'm going to take my actual information measure with my independent variables and my target variable. And then I'm going to calculate the information measures with my independent variables and all of my permutations of the target variable. I'm going to wrap them all up into one and am going to compare my actual information measures to all of my information measures from the permutations. Now, when we permute, we absolutely know that these are random, so the information measures that are returned, we know or should have a strong suspect that there should be a random relationship there. So when we're comparing, it's like, how does our actual information measure compare to our random information measures? And then we want to quantify some confidence around that. And so there are a couple of measures that we're going to use. We're going to use a solo p-value, an unbiased p-value, and then something completely unrelated to the permutation aspect. I also want to go over this concept, which you probably may not have heard of. It's combinatorically symmetric cross-validation. So I'm not going to try to repeat that 10 times fast, but I will say it definitely more than one time. Okay. So from a visualization perspective, what does this look like, right? So we have our matrix X with our independent variables. We have our target variable. Here are our information measures that we're going to use. Mutual information and uncertainty reduction. Both of those highly leverage the concept of entropy. So if you notice here from an entropy perspective, I have this sub I. So this sub I means that I am going to do something that might not necessarily be all that well advised if you're a purist. I'm going to discretize a continuous variable. So it's not a perfect feature evaluation, it's a fast feature evaluation talk. So in that case, right, I'm going to choose the number of bins that I'm going to discretize that into. The mutual information formula here, again, you can see highly leveraging entropy, right? The entropy of our x variable, entropy of our target variable, and then the joint entropy. And so the formula for uncertainty reduction, if you notice, actually is very similar to mutual information. It's basically your mutual information divided by your entropy of your target variable. So what does that mean, right? Here's our little diagram for mutual information, right? Where the pink part, right? That whole entire pink part is your entropy of your independent variable. The, I'll say blue part, is your entropy for your target variable, and then the mutual information is going to be what's overlapped. So the uncertainty reduction is going to be a value between 0 and 1, and if you can imagine, the uncertainty reduction is actually more targeted exactly towards your target variable. Because if this joint mutual information is almost covers the entire entropy, then you know that that particular independent variable actually explains or helps contribute to a lot of the entropy of your target variable. So, okay, so our information measures, and yeah, if you I'll keep going on this, but you can ask questions about this at the end. Okay, our visualization for how the information measures are calculated. We're going to start off with, we have our matrix X with all of our independent variables. We have our target variable Y, and then our info array is going to be our array of actual information measures. And basically, right, we're going to use the observations of our x1 independent variable, of the target variable, and that is going to produce a single information measure. Then we're just going to move through each of the independent variables and populate that entire array. Now, the beautiful thing about this is, all of those information measures are completely independent of one another. So a perfect opportunity for parallelization if we have an underlying framework that can accomplish this. Likewise, we're going to go to our permutation, our original independent matrix, our permutation matrix, and take the information measures from all of our independent variables and our permutations of our target variable and populate these as well. Now, again, similar to the original target variable, all of these are going to be independent calculations. If we have a framework that can accomplish this, then that can accomplish this in a parallelized fashion, we're going to be in good shape. So at the end, we're going to combine both of these, right? Our initial actual information measures and our matrix of what we know to be random information measures, and we're going to do some comparisons of them. So I'm going to go through the confidence measures on here. So the first one is our solo p-value. So the solo p-value is what you would normally think about when you're trying to do assess confidence. And in this case, right, we start off with our null hypothesis, and the null hypothesis is really basically that our variable has no more information than a completely random variable. So so we want to look for if the actual information measure is equal to or below what we know to be a random permutation measure, then we're going to add 1 to our count, because then that supports our null hypothesis that it's worthless. So what we want to look for is a very low value, because then we know across all those random permutations that we are performing better than what a random information measure would be. So again, we're just taking that for that particular variable, all the random permutations measures for that particular variable. So again, basic premise, if a variable can't perform better than a known random relation, then it's probably not worth considering. I underline probably here. Why? Because you have your bivariate and multivariate relationships. So I think one of the famous examples is like height and weight determining obesity. Right? If you look at either of those two individually, it's not going to show up. You combine them both, and there's more information in that. So again, there's plans to build in some bivariate relationship testing as well too into this package. Okay, the unbiased p-value was something interesting. Again, don't really see this discussed too much in the wild, but now, right? Not only did I take random information measures for this variable, but I took it for all of my variables involved. So what I'm going to do, I'm going to make this an even a stronger case to for meaningfulness on my actual information measure. And I'm going to look at, throughout each permutation, I'm going to take my max information measure, and I'm just going to create a single array, and then I'm going to say, okay, how does my actual information measure stack up to like my best performing random information measure, and then perform out of that same p-value concept of like I'm looking for a low p-value score to say that this is going to be better than the strongest relationship. So from a statistics perspective, I think the first talk, Kathy, and even the second talk, from Nathan, talked about doing all of these different iterations and then having to correct for that. So in statistics, there's a concept of a Bonferroni correction, which depending on the degrees of freedom that you have in the problem that you're trying to solve, you need to adjust your p-value accordingly. What this unbiased p-value does, it's almost like a built-in Bonferroni correction, right? Because now you're using a ton of different random information measures from random permutations to account for a stronger relationship from being random. So I kind of like this, and you'll notice as I go through some like live demo examples where the discrepancy between the solo p-value and the unbiased p-values lie. So the combinatorically symmetric cross-validation measure. This one does not include permutations. This will just include your target variable and all of your independent variables. And this one I found to be quite interesting. And what it does is it does a good job of separating your top half of your variables from your bottom half of your variables. So what we're going to do is we're going to divide our data set into an even number of folds. And that's the recommended numbers 4, 6, or 8. And you'll see a reason why we want to keep it to a somewhat maintainable number. We're going to take half of the folds and label them as our in-sample data set, and the other half of the folds as our out-of-sample data set. So in this particular case, I've said fold 1 and fold 2, they are going to be my in-sample. Fold 3 and fold 4 are going to be my out-of-sample. I'm going to take the information measure from my in-sample folds, and I'm going to compare that over the median value from my out-of-sample folds. Again, a good way to determine top half from bottom half of variables. If you're wanting to kind of create the most parsimonious data set of variables to put into a simple baseline model, this is a great method. Then what we're going to do is I'm going to repeat this same process for all possible fold combinations. So when I have four folds, it's 6 combinations, 6 folds, 20 combinations, 8 folds, 70 combinations, and I'm going to create a very similar, this p less than or equal to median value. And so below I gave an examples of just the different folds for when I have 4, so for the 6 combination. Okay, and again, my confidence measure then is proportion of times my in-sample information measure is less than that median information measure. Okay, it's within a single fold combination, but then accumulated across all fold combination pairs. So again, I really hadn't seen this discussed too much anywhere, but it's, again, if you're trying to separate a top half from bottom half, variables that you might want to put into a simple model, this is something that could be incredibly useful. So, history of my Python implementation. I probably started off doing this about 4 years or so ago because I wanted a framework that I could eventually extend this to GPUs, right? If I'm like super high dimensional data sets, then I might want to do more than just 100 permutation reps. I might want to be able to do 1,000. So my history first, I started off with NumPy and Pandas. I did some nested for loops, and man, that took a long, long time. And I was like, okay, I'm not going to get anywhere with this. Then I went to scikit externals, pulled out joblib multiprocessing, and I got a time improvement with multiple processes. But what I also saw, again, this is a couple of years ago, I think maybe they've made some improvements to that. I saw a memory explosion because it started copying. You know, I'm dealing with a high dimensional data set anyway, and I'm just sitting there copying, making copies of my data set, so that didn't start to become quite unmanageable. But then I found out about the parallel accelerator functionality where I could sit in a single memory space. So I get LLVM compiled code for the platform that I'm on. I get multi-threaded parallelization, I don't get any data copying, and Numba's doing some great jobs in terms of making this extensible to GPUs. Just to show you how easy it is to implement, right? Here is my mutual information code, and this is pretty much just native Python code. There's only a couple differences here, right? I wrap it with a numba.jit decorator. I add the parallel equals true, and then my for loop, rather than adding it by range, I say numba.prange, and then make sure that the guts of my code of what I'm doing here, that each one of those cases are independent of one another, that they're not stepping on each other. And this is it, right? However many threads your machine has or is capable of capable of executing on, like this is all it takes. And so I've always said, like, embarrassingly parallel solutions should have an equally parsimonious solution. And so it's I felt like, hey, they're absolutely heading in the right direction with making it this simple to create parallelizable code. So the Python class that I built out, and I wanted to describe a couple of functionality pieces with that. So the class is pandas compatible. So one of the things I wanted to be able to do, I wanted to be able to preserve column names. So typically, right, if you just work in the scikit-learn world, you lose columns because it's just a NumPy matrix. So I wrapped it with some pandas functions in order to preserve column names. I also attempt to do some smart handling of data types. And so that includes just regular continuous numeric, object categoricals, and I even want to do this to date time and cyclical. So right, there's ways to represent cycles in time with sine and cosine. That's going to be part of what I build out from a bivariate functionality. It's scikit-learn compatible, so it inherits selector mixin. I have to admit, I haven't tried it in a pipeline process yet, but it does use a function that selector mixin requires, which is get support, and I'll show you guys that as I go through this. I've also added some selector recipes, or a concept of hey, how might I want to use this as part of a pipeline, right? Basically elevate the certain variables into a model building process. So for this particular talk, I built out two: univariate unbiased, which uses the unbiased p-value, and then univariate CSCV, which uses that p less than or equal to median value as well as that unbiased p-value. I've also implemented multiple information measures. So what I talked about initially was this discrete method, which is more or less a standard method of doing information calculations. But then also in scikit-learn, there's this KNN based, and it's based off of these two papers. And so if I'm going to make this fast and parallelizable, I basically had to port Jake Vanderplas's wonderful binary tree library that he has in scikit-learn all into numba so that I could get complete parallelization. What I found out in the process is, I think about 3 or 4 years ago, he wrote a gist of like, well, numba's just not quite there yet. Some of the advances that they're making, I noticed that my k-nearest neighbors implementation was about 25% faster than the Python version that's in scikit-learn. And then doing querying of the trees, it was upwards of about 10 times faster than the Python version in scikit-learn. So numba is making some great strides. And I know that, at least I had heard rumors that potentially it might become a dependency as part of scikit-learn in the future because people are getting some great performance with that. But don't quote me on that. I'm not part of the scikit-learn community. So the parameters that I have for this, I have my constructor, which is my selector recipe, and I also have added the possibility for some imputation. And this actually adds a lot of time to the process. So if you already have a pretty clean data set, this will just you don't need to do this, and you can save on some time. From a fit perspective, if you need to manually discretize columns or treat them as discrete variables, so think of like area codes, zip codes, things like that that may be represented as numbers, but you want to treat them as discretes. You can manually call those out as part of the fit function. The method, discrete versus KNN. The different measure that you want to do, mutual information or uncertainty reduction, the number of bins that you want to use, the number of reps, and then the number of CSCV folds that you might want to use as well too. So here is information about my GitHub repo with the code and with some example demo notebooks. It is not pip installable yet. That's primarily because I'm using some of the leading, bleeding edge numba functionality, which is in their one of their recent dev versions. But in order to get that, I'll document this in the GitHub repo. You would use your conda update conda so that conda knows about that new version, and then you would update numba accordingly from the numba channel. So here's what the code looks like. In this case, I'll go ahead and run through this example. Actually, I'm going to run it on Domino as well too, our Domino instance at Dell. I'm using a data set from, it was a crowd analytics competition with the Australian Open that used Hawkeye positional data of both the ball and the players, and was attempting to determine whether the play ended as a winner, an unforced error, or a forced error. And it's not huge, it's just 5,000 observations and 24 columns. But it was a nice combination of Boolean variables, categorical variables, and continuous variables. And so wanted to be able to run that. So in this case, load that in as a pandas data frame. Put the selector recipe in, and my imputation, and whether I want to spit out some additional time metrics. I have a verbose there as well too. And then the fit method call. So all in all, it took 89.2 seconds. I also threw out, there were some columns. I do some automatic detection for whether you have a single value in one column, because that's not going to be meaningful to really use anyway. So so I will automatically throw those out. And here's what the output looks like. So in this particular case, you come back here. I did not have any CSCV folds, but I ran it again, so I actually kind of cheated so that I could produce this P median column. And so in this case, what you see, you have some solo P values that are all relatively low, which means that they're performing better than random. The actual the information measure, that's listed there. And the unbiased is also low as well too. And here's where you can see kind of some of the discrepancy between top half and bottom half of variables. Unfortunately, this would have been too small. I didn't know this was going to be like a really nice size screen. Otherwise, I would have put them all in there. But there are 24 total variables, and so that's why you see this kind of cut off. But you do see a relatively clear distinction between this 13 and below, that there is a kind of a top half and a bottom half when looking at that combinatorically symmetric cross-validation method. So how do you use this, right? And like first and foremost, if you're dealing with a very high-dimensional data set, I think this is a great place to look when you're trying to do some initial exploratory analysis. I know one of the things that we also use Tableau in our group, and one of the things that's, okay, let's throw our data set into Tableau and then just start dragging all of the variables in and start looking at things, and it's like, okay, wait, there's got to be a better way of not, looking at all 200 variables that we threw in. There's got to be a better place to start. So I think this is a great method that can get you, like, in a very short amount of time, a good place to start directionally from the, from an EDA perspective. And it's basically would just be one call, right? You load that in as a pandas data frame, and you would just call the function, add in your data frame, dot information, and it'll return what was on the previous slide, and that's a good place to start. The other thing that Dr. Masters describes in some of his texts, it's actually a way to potentially build a smarter and quicker baseline model. So one of the things that he recommends, right, is to retain some of your variables that have low unbiased p-values or solo p-values. Also the ones that retain a p-median value. His magic number that he recommends is less than or equal to 0.2. And then build an elastic net model with that, which is highly ridge in nature. So your L1 ratio is 0.1, and then doing some cross-validation for your optimal alpha. So in scikit-learn terms, that's like lambda from the original GLMNet paper. But this is an interesting way to think about, hey, if I just need to get something out there fast and start comparing other more advanced models to, can it do better than this? Narrow down your variables. So the regularization effect of having fewer variables in your model could be really good in terms of out-of-sample performance. And so, again, an interesting perspective of how he uses some of these methodologies and some of the models that he builds. Some of the future work that I'd like to do, I want to fully incorporate bivariate screening just to make it as robust as possible. I also mentioned earlier, like, I want to support the date timestamp because I think there's a lot of information that's present in your timestamps from a cyclical perspective. So you think, okay, like hourly or daily or monthly or weekly. I think those are all possible with this, and now there's a way to kind of compare those cyclical features using sine and cosine and bivariate screening, combine those with the univariate, and it's all somewhat apples to apples. Want to add some GPU functionality? I know there's some memory optimization to do, and of course, actually the add documentation and test I should probably put at the front of the list so that people know how to use it. Are there any questions so far? There's got to be some questions. Yes.
I was curious, have you done any sensitivity analysis against this versus Bonferroni? My limited experience with it was that it makes sense in theory, but it seemed like a little too punitive when I tried it. So I was just curious if this is as strict, not as strict, or just kind of how much it compares.
So I don't have empirical evidence on this, but I think it's actually probably even stricter. I think it depends upon the size of your data set, honestly, right? So if you think about how many variables it's having to go through, I mean, if you have 1,000 variables, then you're taking the max out of each one of those, it could actually be much more restrictive. Or at least for me, it makes sense that it could be much more restrictive. So in that sense, yeah, I would say maybe be careful because it might be too restrictive if you just use the unbiased. But any other questions? Yes?
How do you choose the number of bins?
Okay, so that's a good question as well too, and I think is somewhat arbitrary. What Dr. Masters recommends is about 3 to 5. That should get you along the way. Now, from a continuous variable space, there are actually some, probably should put on my to-do list. There's a method from the late 90s called adaptive partitioning, which if you're dealing with a continuous variable, with 2 continuous variables, both your target and your independent variable, there are some smart methods to get some non-linearity mutual information measures using that. And that's ultimately what I would like to put in there. Again, you start narrowing down the bin sizes in order to get those non-linearities, it's going to take longer. So one of the ideas just behind straight discretization is that you that it's going to be fast. And it's going to get you more or less in the neighborhood. But it could be 3, 5, 10, basically whatever you're willing to tolerate on that.
If there's correlation between subsequent y values, wouldn't that have some impact on your permutations in your data set as opposed to a purely...
Yes. And so there are some methods that Dr. Masters proposes in terms of how, like, if you do see like autocorrelation between that, like how to adjust for that. And so I don't have that built into this, but I guess part of my grander plans. But no, absolutely, that's a really good question. I mean, because right, you're going to see that if you're dealing with time series stuff for sure. Yes.
So when you say high dimensional, you don't necessarily mean where p is greater than n. Do you just mean when n is large? Or?
Yeah. So if you're interested in that particular case, I highly recommend that data mining in C++ book, because he describes a method that he uses when you have n is, I guess, substantially greater than p. So where you have more independent variables than you have observations. I normally don't deal with that space, but I know, especially like in bioinformatics, that is useful or is something that has to be dealt with. And there's a pretty interesting method that he uses to go do that, and it's discussed in one of his texts. So this is mainly when you have a lot of observations, dealing with more of a big data problem. So yeah, that's it. If you have any other questions, feel free to come and find me during the conference.